Our universe is a magnificent and deceptive place. The stars and galaxies we can see might be just a tiny fragment of a much grander reality. We are about to journey through 30 mind-bending theories that peel back the cosmos like an infinite onion, revealing layers of existence you have likely never considered. By the end, you will possess a new framework for understanding everything from the force accelerating cosmic expansion to the very nature of consciousness itself. What if the Big Bang was not the true beginning? And what if dark matter is not a particle but a shadow from another dimension? What single question about reality keeps you up at night staring at the stars? This grand deception begins with a single, startling possibility. Our entire cosmos, with its billions of galaxies, might be nothing more than a solitary bubble floating in a frothing sea of other universes. This is the multiverse hypothesis, and it is not just science fiction. It emerges from the edges of our most robust scientific theories. One compelling version arises from cosmic inflation, the idea that the early universe underwent a brief period of explosive expansion. According to this thinking, this inflation might not have been a one-time event. It could be eternal, a process that stops in some regions to form a universe like ours, but continues forever in the larger background. Each of these stopping points becomes its own separate bubble universe, potentially with its own unique set of physical laws and constants. In this inflationary multiverse, some bubbles might have stronger gravity, making stars burn out in an instant, while others might have no atoms that can stick together. Reality becomes a cosmic lottery of unimaginable variety. Yet there is another, even more intimate kind of multiverse. The quantum many-worlds interpretation suggests that every time a quantum event has multiple possible outcomes, the universe does not choose one. Instead, it splits, dividing into branches where every possibility is realized. In one branch, you decided to watch this video. In another, you clicked away. Both versions of you are equally real, living out the consequences of every minute decision on an endless, branching tree of reality. The philosophical weight of this is staggering. It challenges our very notion of choice and identity. Are we the architects of our lives, or are we merely walking one path in an infinite garden of forking paths? The idea of countless other versions of ourselves living different lives is both terrifying and awe-inspiring. It suggests a cosmos of such profound depth that our own story is just one sentence in an endless library. But this branching sea of universes is not the only way to hide deeper layers of reality. The very fabric of our cosmos might be woven from components far stranger than tiny points of matter. Imagine the universe is not built from particles but from music. This is the elegant yet complex proposition of string theory. It suggests that the most fundamental entities in existence are not zero-dimensional dots, but incredibly tiny, one-dimensional loops of energy vibrating like the strings of a violin. Just as different vibrations of a violin string create different musical notes, the distinct vibrations of these cosmic strings give rise to the different properties of every particle in the universe. An electron is one note, a quark is another, and the photon is yet another. In this symphony of strings, the entire universe is an orchestral performance on the smallest possible scale. For this beautiful idea to work mathematically, however, the universe cannot have only the three spatial dimensions we know so well. String theory demands extra dimensions of space, perhaps 6 or 7 more, curled up into shapes so minute that we cannot perceive them. Think of a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl on its surface, you would discover a second dimension curled around the hose's circumference. Our entire reality might be like that hose. We are macroscopic creatures, only aware of the large, expansive dimensions, while the tiny, curled-up dimensions dictate the fundamental rules of physics right under our noses. This compactification of extra dimensions is one of the theory's most profound concepts. It is an attempt to answer physics' greatest challenge, unifying the colossal world of gravity, described by Einstein's general relativity, with the bizarre quantum realm of the very small. String theory elegantly brings gravity into the quantum fold by proposing that the graviton, the hypothetical particle that carries the gravitational force, is simply another vibrational mode of a string. This suggests a reality of breathtaking complexity, where what we perceive as empty space is a multidimensional landscape of incredible intricacy, its hidden geometry shaping everything from the birth of stars to the bonds between atoms. Yet even these vibrating strings might be playing their symphony on a surface we cannot see. The holographic principle proposes a reality so strange it challenges our most basic assumptions about space. It suggests that our seemingly solid, three-dimensional universe with its stars, planets, and people could be nothing more than a hologram, a magnificent projection from a two-dimensional surface at the cosmic edge. Think of a security hologram on your credit card. The flat, shiny surface encodes all the information needed to create a stunning three-dimensional image. The holographic principle argues our universe works in a similar way. All the information that describes everything happening within our three-dimensional space, every star, every thought, every event, is actually encoded on a distant, two-dimensional boundary that surrounds us. We are not just in the universe, we are a picture painted on its ultimate wall. This radical idea did not emerge from pure speculation. It grew from the fiery logic of black holes. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, which is a measure of its hidden information, is not proportional to its volume as you might expect. Instead, it is proportional to the surface area of its event horizon. This was a profound clue. It suggested that all the information about everything that ever fell into a black hole is not lost deep within its volume, but is somehow smeared across its two-dimensional surface. Leonard Susskind and Gerard T. Hooft took this stunning insight and ran with it, proposing that if it is true for a black hole, it might be a fundamental property of the universe itself. The information that makes up your body, your memories, the very device you are using right now, might be etched onto the fabric of space-time at the boundary of the observable cosmos. We are living inside a cosmic projection, a reality that feels vast and deep but is ultimately a shadow play. This forces us to confront a deep mystery about the nature of information itself. Is information the most fundamental ingredient of reality, more basic than matter or energy? If our three-dimensional world is just a convenient way to read a two-dimensional code, then what does that say about the solidity of the chair you are sitting on or the ground beneath your feet? The universe begins to feel less like a physical object and more like a cosmic data storage device, and we are the conscious patterns emerging from its immense hidden hard drive. Perhaps the most tangible evidence for hidden layers of reality is the ghostly pull of dark matter. We know it is there because we can watch galaxies spin at impossible speeds without flying apart, held together by the gravitational grip of something invisible. For decades, the hunt has focused on finding a new, exotic particle. But what if we are looking in the wrong place entirely? Imagine a universe existing right alongside our own, a parallel realm with its own stars, planets, and galaxies made of ordinary matter. Now picture that this entire cosmos is tucked away, curled up in one of those tiny, compact dimensions proposed by string theory. The matter in that other dimension would be completely invisible and untouchable to us. Its light could never cross the dimensional barrier to reach our eyes, and its atoms could never bump into ours. But gravity is different. According to Einstein, gravity is not a force in the traditional sense. It is the curvature of space-time itself. If two universes are connected by a shared fabric of space-time, then gravity could be the one force that bleeds through. The massive objects in that hidden dimension would warp the geometry we both share, and we would feel that warping as an inexplicable, ghostly gravitational pull. We would name this mystery dark matter. This elegant idea reframes one of cosmology's greatest puzzles. The reason our most powerful particle detectors have found nothing is not because dark matter is shy, but because it is not here with us. It is all around us, yet forever out of reach in a direction we cannot point. Every galaxy we see could be shadowed by a twin made of hidden matter, their combined gravitational fields locking them in a cosmic dance we can only sense indirectly. This theory turns the universe into a vast, multi-layered sculpture, where we are only perceiving one facet of a magnificent, multi-dimensional whole. This invisible force, dark energy, presents a paradox even more baffling than dark matter. We watch as galaxies rush away from each other at ever-increasing speeds, as if space itself is being stretched from within by some unseen hand. The leading explanation for this cosmic acceleration is the cosmological constant, a concept so simple and yet so perplexing it has haunted physicists for over a century. It is the idea that empty space is not truly empty. Instead, the vacuum of space possesses a fundamental, intrinsic energy. This vacuum energy exerts a negative pressure, causing the very fabric of the cosmos to push itself apart. Think of it as an anti-gravity force woven into the bedrock of reality, a constant and relentless pressure that was negligible in the dense early universe but now dominates its evolution, steering its fate toward an ever colder, more isolated future. This single number, the value of the cosmological constant, is perhaps the most embarrassing problem in all of theoretical physics. When scientists try to calculate how strong this vacuum energy should be based on quantum theory, they arrive at a number that is catastrophically wrong. Their prediction is off by a factor of 1 followed by 120 zeros. It is the worst mismatch between theory and observation in the entire history of science. This staggering failure suggests we are missing something profound. Either our understanding of quantum mechanics is deeply flawed when applied to the vacuum of space, or dark energy is not a constant at all. This is where an alternative theory emerges, one with a name from ancient philosophy, quintessence. Unlike the static cosmological constant, quintessence proposes that dark energy is a dynamic field, a kind of fifth fundamental force that permeates all of space. Its strength could change over time, slowly evolving and interacting with matter in subtle ways we have not yet detected. This opens up dramatic possibilities for the ultimate fate of the cosmos. A cosmological constant dooms the universe to a slow, cold heat death. But if dark energy is quintessence, the future could be far more violent. This field could eventually strengthen, leading to a big rip where the fabric of space-time is torn apart from galaxies down to atoms. Or it could weaken and reverse, pulling the universe back together in a cataclysmic big crunch. The true nature of dark energy is more than a puzzle about expansion. It is a direct window into the deepest laws of physics, a clue that the vacuum of space itself holds a secret, active layer we are only beginning to sense. The violent beginning of our cosmos might have been a quiet collision in a higher dimension. Before the Big Bang, the story of our universe could have been written on a vast, multidimensional membrane, a brain for short. Picture our entire three-dimensional reality as a single, immense sheet, floating within a higher dimensional expanse called the bulk. We are trapped on this brain, unable to perceive or move into the bulk, but other brains could be drifting nearby in this hidden ocean of space. The ekpyrotic universe theory proposes that our Big Bang was not a singular eruption from nothingness, but the result of a gentle collision between our brain and a neighboring one. When these two cosmic sheets brushed against each other, the impact infused our space with an immense amount of energy, heating it to a phenomenal temperature and seeding it with the matter and radiation that would later condense into galaxies. This was not a bang but a bounce, a rebirth from a previous phase of existence. This idea naturally leads to a cyclic model of the cosmos, an endless rhythm of creation and destruction. After the collision, the brains move apart, our universe expands and cools, and eventually dark energy might pull everything so far apart that structure fades away. But then, drawn together by some fundamental force, the brains approach once more, leading to another collision and another new beginning. In this view, the Big Bang was not the ultimate beginning, but merely the latest chapter in an infinite cycle. This provides a powerful alternative to the theory of cosmic inflation, offering an explanation for why our universe appears so uniform and flat without requiring a period of hyper-fast expansion. The pre-Bang universe is not lost to time. It is simply hidden in other dimensions, its history etched onto the geometry of the brains as they move through the bulk. We are living in the aftermath of a quiet, multidimensional touch, a cosmic event whose echoes are written in the oldest light we can see. The quiet collision of cosmic membranes hints at a universe built on deeper structures, but what if those structures are not physical at all? The simulation hypothesis presents a possibility that is both terrifying and intellectually seductive. It suggests that our entire cosmos, from the most distant quasar to the feeling of warmth on your skin, is not base reality, but an artificial construct, a simulation running on a computer of unimaginable power in a civilization far beyond our own. This is not a new idea from science fiction, but a serious argument put forward by philosophers like Nick Bostrom. His reasoning follows a logical trilemma. He proposes that at least one of three statements must be true. Either virtually all advanced civilizations go extinct before developing the capability to run such simulations, or they have no interest in creating simulations of their ancestors, or we are almost certainly living in one. If a post-human species ever reaches a technological level where it can harness the computational power of entire planets or stars, and if it has any desire to run detailed ancestor simulations for research or entertainment, then the number of simulated universes would vastly outnumber the one base reality. Statistically, any conscious being, like you or me, would therefore be far more likely to be a simulated mind in one of those countless programs than an organic brain in the original world. This is a modern version of the brain in a vat thought experiment, scaled up to a cosmic level. Could we ever spot the glitches in this grand simulation? Some have looked to the strange rules of quantum mechanics for clues. The universe appears to be smooth and continuous, but what if we probe to the very smallest scales? In computer graphics, when you zoom in too far on an image, you eventually see the individual pixels. The laws of physics might have a similar resolution limit. There is a fundamental unit of length known as the Planck length, a distance so minuscule that the very concepts of space and time break down. Could this be the pixel size of our simulated reality, the smallest possible increment that the universe's rendering engine can process? The bizarre phenomenon of quantum entanglement, where two particles instantly influence each other across vast distances, might also be explained not by spooky action but by optimization. A clever simulation would not need to calculate the state of every particle independently. It could use a shortcut, linking them with underlying code to save processing power. Finding evidence of this cosmic code is the ultimate challenge. Perhaps the constants of nature, like the speed of light or the strength of gravity, are not fundamental truths but finely tuned parameters set by the programmers. Maybe we will one day discover a mathematical bug, an inconsistency in the laws of physics that points to a lazy programmer or a rounding error in the source code. This idea forces a profound re-evaluation of what is real. If our universe is a simulation, then the quest for a theory of everything is not a search for God's mind, but for the programmer's blueprint. Our struggles, our joys, and our consciousness itself would be phenomenally complex algorithms running on a substrate we cannot comprehend. Are we the creators or are we the created, living our lives in a universe that is, at its heart, a stream of pure information? This unsettling dance between quantum choice and identity leads us to a deeply personal and perhaps terrifying implication of the many worlds interpretation. Quantum immortality is a thought experiment that pushes the logic of branching realities to its absolute limit. Imagine you are part of a dangerous experiment, strapped to a device that is triggered by the random decay of a single radioactive atom. There is a 50% chance the device will fire and kill you in the next minute. You press the button. According to the many worlds interpretation, the universe instantly splits. In one branch, the atom decays and you die. In the other branch, it does not and you live. Now, from your perspective as the conscious observer, which branch do you experience? You can only experience the timelines in which you are alive to have an experience. From your first-person point of view, it would seem as though you miraculously survive, no matter how low the odds become. You could repeat this experiment 1,000 times, and from your subjective standpoint, you would always find yourself in the branch where the atom stubbornly refuses to decay. It would appear as if you are immortal, not because your body is invincible, but because you are forever branching into the realities where you continue to exist. This is not a recipe for a superhero, but a logical ghost in the machine of reality. The you in the other branches, the ones where the accident happened or the illness was fatal, are gone. But your stream of consciousness, the one you call yourself, seamlessly continues along the path where survival against all odds is always possible. This forces us to confront the nature of the self. What are we really? Are we a single, continuous thread of awareness, or are we a constantly splintering entity with countless versions dying all the time while one lucky path persists? The you reading this sentence is not the only you, but you are the only one that this particular consciousness will ever know. The implications stretch far beyond dramatic experiments. Every near miss in traffic, every recovered illness, every time you cheat death by sheer chance could be interpreted through this bizarre lens. You are not necessarily lucky. You are simply the version of you that is always left standing to tell the tale, while an infinite number of your other selves in parallel worlds are not so fortunate. This idea paints a cosmos of profound solitude, where your conscious experience is perpetually shepherded away from death, no matter how ancient you become or how many cosmic catastrophes befall the universe. It suggests a reality where the end of your story is not a final period, but an endless ellipsis, branching forever into futures you can scarcely imagine. This bizarre thought experiment forces us to question the very reliability of our memories and the world around us. Named after the physicist Ludwig Boltzmann, the paradox emerges from the laws of thermodynamics and probability. In an endless and ultimately random universe, given enough time, even the most wildly improbable events are not just possible, they are inevitable. The spontaneous formation of a fully formed, self-aware brain, complete with false memories of a past and a seemingly real present, is statistically far more likely than the formation of an entire, orderly cosmos spanning billions of light years. The odds of a single, conscious brain popping into existence from the quantum foam of a vacuum are astronomically bad, but the odds of our entire complex universe are infinitely worse. So, if you are betting on probability, you should not be a person in a vast universe. You should be a lone, disembodied brain, a Boltzmann brain, floating in an endless, empty void, hallucinating everything you think is real. Every star you have ever seen, every person you have ever loved, every memory you hold dear could be an elaborate phantom, a perfect simulation generated by a mind that formed moments ago from pure chaos. This is not just a philosophical curiosity, it is a direct challenge to our best cosmological models. An eternally inflating multiverse, or a universe headed for heat death, provides the infinite time and space required for these freak fluctuations to occur, not just once but in countless numbers. The number of these isolated, hallucinating brains should, by the math, vastly outnumber the number of real, embodied observers in structured universes. So why do we find ourselves in a coherent, ordered reality, and not as a fleeting thought in the dark? This is the paradox that keeps cosmologists awake at night. Some propose that our current understanding of the cosmos is fundamentally flawed, that we live in a special universe that somehow prevents such chaotic fluctuations. Others suggest a more unsettling resolution, that we cannot trust the conclusion precisely because we are coherent observers embedded in a consistent world. The very fact that we perceive a stable, logical universe might be the only evidence we need to prove we are not Boltzmann brains, because a randomly generated mind would be drowned in nonsense and contradiction. Yet the doubt lingers, a ghost in the machine of cosmology, forcing us to confront a terrifying possibility. The deepest layers of reality might not be hidden in other dimensions, but in the fragile, uncertain nature of our own consciousness. Our journey through the cosmos reveals structures that seem to defy logic, and none more so than the theoretical twin of the black hole. A white hole is conceived as its exact opposite. Where a black hole's event horizon is a point of no return, a one-way street into oblivion, a white hole would possess a horizon that is utterly impenetrable from the outside. Nothing, not even light, could ever cross in. Instead, it would violently expel matter and energy in a continuous, radiant outburst, a cosmic geyser of creation. If a black hole is a drain in the fabric of space, a white hole is a fountain. While black holes are predicted by general relativity and we have overwhelming evidence for their existence, white holes remain purely mathematical curiosities. No astronomical object we have observed behaves in this way. The laws of physics as we know them suggest that while a white hole is a valid solution to Einstein's equations, the process of forming one in our universe is virtually impossible. They represent a universe that is fundamentally time asymmetric, a one-way street where collapse into a black hole is allowed, but the reverse process is not. Yet their theoretical existence opens a door to even grander possibilities. What if a black hole and a white hole are not separate objects, but two ends of the same cosmic tunnel? This is the breathtaking concept of an Einstein-Rosen bridge, more popularly known as a wormhole. Imagine space as a vast, two-dimensional sheet of paper. If you wanted to travel from one point to another, the normal route would be a long line across the surface. But if you could fold the paper, bringing those 2 points together, you could punch a hole through the gap, creating a shortcut. A wormhole is that shortcut through the higher dimensional bulk of space, a tunnel connecting two distant regions of our universe, or perhaps even more fantastically, two entirely different universes. This is not just a tunnel through space, but potentially through time as well, fulfilling the ancient dream of a time machine. The gravitational extremes at the center of a black hole could, in theory, warp spacetime so severely that it connects to the erupting throat of a white hole in another realm. You would fall into the black hole, and instead of being crushed at a singularity, you would be ejected from the white hole, perhaps billions of light years away or in a completely different cosmic epoch. The challenges, however, are as immense as the promise. The primary obstacle is stability. The tunnel of a wormhole, according to our current understanding, would be incredibly unstable. It would likely pinch shut the instant anything, even a single photon, tried to pass through, collapsing faster than the speed of light. To keep it open, you would need a form of exotic matter with negative energy density, something that exerts a kind of anti-gravity, propping the throat of the wormhole open against its own immense gravitational pressure. Whether such matter can exist in any useful quantity is one of physics' great open questions. These theoretical structures hint at a hidden architecture to the cosmos, a web of potential connections woven into the very fabric of spacetime. They suggest that the universe might be filled with these cosmic shortcuts, most of them microscopic and fleeting, blinking in and out of existence at the quantum scale. Perhaps the key to unlocking the universe's deepest layers is not to build a bigger telescope, but to learn how to stabilize these natural gateways, turning mathematical phantoms into pathways to the stars. These cosmic shortcuts offer pathways to the stars, but the very space they traverse might be doomed from within. Phantom energy is a particularly vicious flavor of dark energy, a hypothetical substance that does not merely push the universe apart, but actively strengthens as it does so. Unlike the steady pressure of a cosmological constant, phantom energy would grow more powerful over time, its repulsive force becoming absolute. The consequence of this escalating dominance is a cosmic doomsday known as the Big Rip. Imagine the expansion of space accelerating not just between galaxy clusters, but everywhere. First, the gravitational glue holding clusters of galaxies together would be overwhelmed. The Milky Way would watch as all other galaxies vanished over the horizon of visibility, leaving us utterly alone in a deepening void. Then, the expansion would turn inward. The force binding our own galaxy together would fail. Stars would be flung away from each other into the ever-widening emptiness. Next, it would target our solar system. The Sun's gravitational grip on Earth would be broken. Finally, in the last terrifying moments, the expansion would become so intense that it would overcome the forces holding matter itself together. Planets, stars, and eventually every molecule, every atom, and every atomic nucleus would be torn asunder. The very fabric of space-time would be shredded, ripping apart the building blocks of reality in a final, catastrophic moment. This theory reveals a hidden layer of cosmic evolution where the vacuum of space itself holds not just energy, but a self-amplifying destructive potential. It suggests that the fate of the universe is not a slow fade to black, but a violent, explosive end where the cosmos literally comes undone at the seams. The existence of such phantom energy would mean that the universe's darkest secret is not matter we cannot see, but a force embedded in nothingness that is waiting to unravel everything we know. The violent end of a phantom energy universe is not necessarily the final word. A cosmos torn to its fundamental threads could be the raw material for a brand new beginning. Sir Roger Penrose's conformal cyclic cosmology offers a breathtaking vision of eternity, where the universe endlessly recycles itself in a cycle of death and rebirth so complete that the unimaginably distant future of one era becomes the hot, dense Big Bang of the next. This is not a collision of brains, but a transformation of scale so profound that the concepts of time and distance lose all meaning. In the final state of our universe, after black holes have evaporated and particles have decayed, only massless energy and an infinitely expanding, empty space remain. Penrose proposes that in this state of maximum simplicity, the universe can be mathematically rescaled or conformally transformed. The endless, cold emptiness of one eon is remapped into the searing, energetic singularity of the next. The end becomes the beginning seamlessly. The evidence for this radical idea, Penrose argues, is written in the oldest light we can see. He points to mysterious, anomalously warm spots in the cosmic microwave background, which he calls Hawking points. These are theorized to be the imprints of supermassive black holes from the previous eon. As those ancient black holes evaporated over trillions of years, they released a final burst of Hawking radiation. In the conformal rescaling that created our Big Bang, that burst was transformed into a circular patch of slightly higher temperature on the very first surface of our new universe. These are cosmic fossils, the ghosts of long-dead giants from a reality that existed before time, as we know it, even began. This leads to the most profound implication of the theory, the preservation of information. If Hawking points are real, then information is not lost in the death of a universe. It is translated, encoded into the hidden conformal geometry of spacetime itself, and passed on to the next cycle. The very structure of reality may carry memories of its past lives, layers of information stacked upon one another through infinite cycles. Our universe's deepest laws and constants might not be arbitrary, but an inheritance from an eternal chain of cosmic reincarnation, a story written in the fabric of space and waiting to be read in the faint glow of creation's first light. The ghost of a Boltzmann brain forces us to question the very nature of our own perception. This unsettling doubt connects directly to one of philosophy's oldest nightmares, the brain in a vat. Imagine your conscious mind, your entire being, surgically removed from your body and placed in a vat of nutrient fluid. Electrodes are meticulously attached to your brain, feeding it a perfectly simulated stream of electrical signals. These signals craft every sensation you believe is real. The warmth of sunlight, the taste of food, the sound of a loved one's voice, all are just data points in an elaborate fabrication. Your body, the world, the universe itself, are nothing but illusions generated by this complex stimulation. How could you ever prove you are not in that vat right now? This ancient thought experiment, debated for centuries, has been supercharged by modern neuroscience and the rise of artificial intelligence. We now know that the world we experience is not a direct feed from our senses. It is a constructed model, a best guess generated by our brain. Your eyes do not see the world, they capture scattered photons, and your brain interprets this data, filling in blind spots and making assumptions to create the seamless, high-definition movie you call reality. Optical illusions are perfect examples of this construction at work, where your brain's model fails to match the raw data. This means we are already living in a kind of filtered simulation, one built by our own neurology. Now consider the rapid advancement of artificial intelligence and virtual reality. We are already creating immersive digital worlds that can trick our senses. It is not a giant leap to imagine a future civilization, or one that exists right now, with the computational power to run a simulation so perfect, so detailed, that the conscious minds within it have no idea they are living in a code-based universe. They would be, for all intents and purposes, brains in a vat, though the vat is a server farm and the nutrients are electrical power. This modernized scenario, a real-world matrix, presents a terrifying epistemological problem. If our reality is a simulation, every tool we have to investigate reality is also part of that simulation. A simulated scientist using simulated equipment in a simulated lab would find simulated evidence for simulated laws of physics. The rules would be consistent because the code is consistent. You could spend a lifetime studying quantum mechanics or general relativity, and you would simply be reverse engineering the programming of your own prison. So how could we ever detect the hidden base layer, the true reality outside the vat? Some look for potential glitches in the matrix, tiny anomalies in the laws of physics. Perhaps there is a fundamental resolution limit to space-time, a pixelation at the Planck scale. Maybe constants of nature, like the speed of light, are not fundamental but are set values, and we might find they are unnaturally fine-tuned for complexity, like parameters chosen by a designer. The bizarre collapse of the quantum wave function could be a processing shortcut, a way for the simulation to only render definite outcomes when they are observed, saving immense computational resources. Yet, even if we found such evidence, could we ever trust it? A sufficiently advanced simulation would be seamless, its very design preventing any detection from within. This leaves us with a profound solitude. The only thing we can be certain of is the fact of our own consciousness, the experience of being. Everything else, from the chair beneath you to the stars overhead, could be an impossibly convincing illusion. The search for the universe's hidden layers ultimately turns inward, becoming a quest to understand the one thing we might truly know exists, the self that is doing the questioning. The solid ground of reality begins to feel like a fragile illusion. This profound uncertainty about our own perception forces a radical rethinking of our cosmic home. Perhaps the entire universe we inhabit is not a vast, independent expanse, but something much more intimate and contained. Our universe might be the interior of a black hole. The Big Bang was not a unique creation event, but the explosive white hole eruption from a colossal, pre-existing black hole in a parent cosmos. This stunning idea emerges from a deep mathematical symmetry. The equations describing the gravitational singularity at the heart of a black hole, a point of infinite density, bear a striking resemblance to the equations describing the initial singularity of the Big Bang. Both represent a boundary where our known laws of physics break down. The theory simply proposes they are the same boundary viewed from opposite sides. From the outside, matter collapses into a black hole, vanishing from one universe. From the inside, that same event is the violent, radiant beginning of another. Our cosmic expansion is not happening in empty space. It is the continued, unstoppable growth of that new space-time fabric itself, stretching from its initial white hole birth. This perspective offers a fresh lens on one of our greatest mysteries, dark energy. The accelerating expansion of our universe could be a natural consequence of this inherited geometry. As matter continues to fall into the parent black hole from its external universe, it injects energy into our cosmos, driving its expansion from the outside in a process called accretion-induced radiation. What we perceive as a mysterious force from within is just the gravitational influence of our cosmic parent. This leads to the most breathtaking implication of all, a cosmic fractal. Every black hole that forms in our universe could, in turn, contain an entire new cosmos within it, bubbling into existence with its own laws and constants. Our universe is not just inside a black hole, it is also giving birth to countless others. Every star that collapses into a singularity might be sowing the seed for a new reality, a new Big Bang in an endless, branching tree of universes. We are not at the top of a cosmic hierarchy, but somewhere in the middle of an infinite cascade of creation, each reality nested within another like an endless set of cosmic matryoshka dolls. This theory redefines our place in the cosmos, suggesting that the grandest structures we see are merely the interior walls of a celestial object in a universe far beyond our own. This elegant nesting of universes hints at a hidden architecture, a deep symmetry that might be woven into the very fabric of reality. One of the most compelling blueprints for this architecture is supersymmetry, a theory so beautiful it has captivated physicists for decades. It proposes a profound and fundamental partnership at the heart of existence. For every particle we know, from the humble electron to the quirky quark, there should exist a massive, undiscovered twin, a superpartner. Imagine a cosmic mirror that reflects our familiar world, but in this reflection, every particle is shadowed by a much heavier counterpart. The electron's partner would be the selectron, the quarks the squark, and the photons the photino. This is not just a duplication of matter, it is the revelation of a perfect, hidden symmetry between the two great classes of particles, the fermions that build matter and the bosons that carry forces. Supersymmetry suggests they are two sides of the same coin, connected by a transformational symmetry we have yet to observe directly. The implications of finding this symmetrical layer are staggering. First, it offers a perfect candidate for the identity of dark matter. The lightest of these superpartners, often thought to be the neutralino, would be stable, electrically neutral, and only interact through gravity and the weak nuclear force. It would be invisible to our telescopes and mostly oblivious to our detectors, a ghostly particle that permeates the cosmos, forming the vast, unseen gravitational scaffolding that holds galaxies together. We would have been living in a universe teeming with shadow matter, a perfect mirror to our own, yet just out of reach. Second, supersymmetry provides an elegant solution to one of physics' most nagging problems, the hierarchy problem. This is the puzzle of why the force of gravity is so unbelievably weaker than the other fundamental forces. The math of our current model suggests that the quantum jitters of virtual particles should drive the mass of the Higgs boson, and by extension the scale of the weak force to an astronomically high value, making our universe impossible. Supersymmetry naturally cancels this effect. The heavy superpartners act as counterweights, their own quantum contributions perfectly balancing out those of their standard model twins, leaving the Higgs mass at the delicate, low value we observe. It is a cosmic balancing act of breathtaking precision. For this beautiful cancellation to work, the superpartners cannot be too heavy. Their masses should be within the range of our most powerful particle colliders. This is why the hunt for these shadow particles has been a primary goal of the Large Hadron Collider. We are essentially shaking the fabric of space-time at unprecedented energies, listening for the echo of a selectron or the whisper of a squark. Their discovery would be a triumph, revealing a symmetrical layer of reality that has been hidden in plain sight all along. Yet so far, the superpartners have remained elusive. This silence is itself a profound clue, forcing physicists to consider that supersymmetry might be broken in a more complex way, or that we must look to even higher energies. The absence of these particles is a mystery as deep as their existence would be, a reminder that the cosmos guards its most fundamental secrets with relentless determination. The profound silence from supersymmetry leaves us with a universe that feels unnaturally balanced. Step back and look at the fundamental numbers that govern reality. The strength of gravity, the force that binds atoms, the mass of an electron. If any of these constants were altered by even a fraction of a percent, the cosmos as we know it would vanish. A slightly stronger gravitational constant, and the universe would have collapsed back on itself in a fiery crunch moments after the Big Bang. A slightly weaker force binding atomic nuclei, and hydrogen would never have fused into the heavier elements essential for planets and life. This delicate arrangement is known as the fine-tuning problem, and it presents a riddle that is impossible to ignore. Why does the universe appear so perfectly calibrated for our existence? This question leads us directly to the anthropic principle, an idea that is as simple as it is profound. In its weak form, the principle is almost a tautology. It states that the universe must be compatible with conscious life because we are here to observe it. We could not possibly find ourselves in a universe devoid of the conditions needed for life, so the very fact of our existence filters the kind of universe we can perceive. It is like a lottery winner marveling at their luck without considering the millions of other tickets that lost. The weak anthropic principle does not explain why the winning numbers were drawn. It only notes that a winner had to exist for the prize to be claimed. The strong anthropic principle, however, takes a much more assertive stance. It suggests that the universe must have properties that allow life to develop within it at some stage in its history. This version hints at a deeper necessity, as if the cosmos was compelled by its very laws to eventually give rise to conscious observers. It edges toward the teleological, the idea that the universe has a purpose or a goal, and that goal is us. This line of thinking inevitably leads to one of humanity's oldest questions. Does this apparent fine-tuning point toward a cosmic designer? For many, the breathtaking precision of the physical constants is the most compelling argument for a divine architect, a master programmer who set the initial parameters to allow for complexity and consciousness. The universe, in this view, is not an accident but a carefully crafted artifact. Yet science offers another, equally staggering explanation, one that returns us to the concept of the multiverse. If our bubble universe is just one of an infinite number in a vast cosmic landscape, each with its own randomly selected set of physical laws, then it is no surprise that we find ourselves in one of the rare habitable ones. In a near-infinite array of universes, every possible combination of constants will be realized somewhere. Most will be stillborn, collapsing instantly or expanding too rapidly for atoms to form. But a precious few will, by pure statistical chance, have the golden ticket. We are not the result of a targeted design, but the beneficiaries of a cosmic lottery with an almost infinite number of losing tickets. Our existence is not a miracle, but a selection effect. We are simply the lucky ones who drew the winning numbers. This debate sits at the crossroads of science, philosophy, and theology. Are we the purpose of the cosmos, or are we a fleeting, random pattern in an indifferent multiverse? The answer may be forever beyond our reach, but the question itself forces a profound humility. The universe is not only stranger than we imagine, it may be stranger than we can imagine, hiding its ultimate nature not in distant galaxies, but in the very laws that allow us to ponder its existence. Our relentless march from past to future feels like the most undeniable truth of existence. Yet physics at its deepest level whispers a heretical idea that time itself may be a magnificent illusion. This is the proposal of Theory 17, that time is not a fundamental river flowing through the cosmos, but an emergent property, a side effect arising from a more basic, timeless reality. The clues lie in our most successful attempts to unite gravity with the quantum world. The Wheeler-DeWitt equation, a foundational piece of quantum gravity, presents a universe frozen in a single, eternal moment. It describes the entire cosmos in one breath, but that description has no variable for time. The equation simply drops out the t for time, painting a picture of a static block where change is not built into the fabric. This timeless wave function of the universe suggests that past, present, and future all exist simultaneously in a fixed structure, much like every frame of a film already exists on the reel. Our conscious journey from one frame to the next is the only motion, the only becoming that is real to us. So where does our powerful, unshakable feeling of time's flow come from? One compelling answer is entropy, the measure of disorder in a system. Think of an ice cube melting in a glass of warm water. The ordered, crystalline structure of the ice gives way to the disordered, random motion of water molecules. This increase in entropy provides a powerful arrow pointing from order to chaos. Our brains, as complex biological systems, may use this increasing disorder as a clock. We remember the past as a state of lower entropy and anticipate the future as a state of higher entropy. This creates the psychological arrow of time, the feeling that we are moving forward. But in the fundamental, timeless block described by physics, this is just a local story, a narrative we construct as our corner of the universe evolves from order to disorder. The Big Bang, with its incredibly low entropy state, may have simply wound up the cosmic clock, and we are living through its long, slow unwinding. Our entire lives, our history, our sense of progress, could be nothing more than a journey up a single slope on an eternal, timeless landscape. This forces a profound question about free will and destiny. If the future is already out there, just as fixed and real as the past, then are our choices truly our own, or are we merely reading lines from a script written in the geometry of space-time? The universe may be a single, breathtaking sculpture, and we are simply the beam of a flashlight moving across its surface, mistaking the illumination of each new detail for the act of creation. This perfect balance of creation from nothing brings us to a theory of breathtaking elegance. The entire cosmos, in all its splendor and complexity, might have a net energy of exactly zero. All the stars, galaxies, and dark matter, everything we consider to be something, could be perfectly counterbalanced by the negative energy stored in the gravitational field that binds it all together. Think of the universe as a vast bank loan. To build a magnificent city, you borrow an enormous amount of money. This borrowed capital represents all the positive mass energy in the cosmos, the stuff of existence. But the debt you owe, the negative balance on the ledger, is the gravitational energy. The more spectacular the city, the larger the debt. In the end, the books balance to zero. You have built a universe from a perfect symmetry of positive and negative. This idea emerges directly from the principles of general relativity. When a star forms from a cloud of gas, it releases an immense amount of gravitational potential energy as heat and light. This energy is negative, and it precisely offsets the positive mass energy now locked within the star. Scale this up to the entire universe, and the math suggests the total sum is nothing. This leads to a staggering possibility. If the universe truly has zero net energy, then it could have originated from a random quantum fluctuation in a state of perfect nothingness. In the quantum realm, empty space is not serene and quiet. It is a seething foam where particle-antiparticle pairs constantly blink into and out of existence, borrowing energy from the vacuum for a fleeting instant before annihilating and paying the debt back. Normally, these fluctuations are tiny and short-lived, but what if, on a cosmic scale, a fluctuation of staggering size occurred, and the resulting positive and negative energies were trapped in the form of a nascent universe? The universe would then be the ultimate free lunch, a fluctuation that never had to repay its debt because the debt and the credit were eternally and perfectly matched. We are not the aftermath of a singular explosion from a divine finger, but the child of a quantum accident, a statistical inevitability in an eternal void. The cosmos hides its ultimate origin not in a fiery bang, but in a perfect, silent balance, a zero written on the fabric of nothingness. That perfect zero hints at a universe born from a quantum spark, but what if the first structures to emerge from that fire were not particles but prisons? The ghostly pull of dark matter might be the collective gravity of countless ancient black holes, relics from the universe's first second of existence. These are not the stellar black holes formed from dying stars. These are primordial black holes, hypothetical objects that could have been forged in the extreme density fluctuations of the Big Bang itself. In that seething, chaotic furnace, pockets of space could have become so unimaginably dense that they collapsed directly into black holes, bypassing the need for a star's life cycle entirely. Their potential masses are a key to the mystery. They could range from the minuscule, with the mass of a small asteroid compressed into a width smaller than a proton, to the colossal, weighing millions of times our Sun. This vast range means they could be everywhere, from the solar system's outer reaches to the hearts of galaxies, completely invisible yet gravitationally dominant. One of the most compelling pieces of evidence for their existence comes from gravitational lensing. When a massive object passes in front of a distant star, its gravity acts like a lens, bending the starlight and causing the star to temporarily brighten. Astronomers have observed these mysterious microlensing events, and while some are caused by known objects, a population of unseen, compact masses seems to be responsible for many others. Primordial black holes are perfect candidates for these invisible lenses. A swarm of these ancient objects drifting through the galactic halo could perfectly explain the observed patterns of flickering starlight. This theory paints a haunting picture of our cosmos. The dark matter halos that envelop galaxies like ours may not be a diffuse cloud of exotic particles, but a vast dark swarm of these primordial black holes. They are the universe's firstborn, the silent architects of cosmic structure whose gravity sculpted the first galaxies and continues to hold them together today. They would be a hidden population, a fossil record of the universe's most violent birth pangs, forever lurking in the darkness between the stars. Their discovery would rewrite our cosmic history, revealing that the very first structures were not stars but shadows. While string theory adds extra dimensions, another path to quantum gravity proposes a universe built from a fabric of tiny, woven loops. Loop quantum gravity takes a radically different approach, suggesting that space and time themselves are not smooth and continuous, but are instead composed of a finite web of discrete, one-dimensional loops. These loops, woven together, form the very fabric of the cosmos in a structure often called spin foam. Space is not an empty stage where events unfold. It is the stage, and this stage has a fundamental, granular resolution. You cannot divide space infinitely. There is a smallest possible unit, a quantum of volume, just as there is a smallest unit of light, the photon. This discrete nature of space-time becomes critical when we rewind the cosmic clock all the way back to the beginning. In the standard Big Bang model, general relativity predicts a singularity, a point of infinite density and temperature where the laws of physics break down completely. It is the ultimate dead end for our understanding, but loop quantum gravity, by its very nature, cannot have infinities. The granular structure of space prevents matter and energy from being compressed into an infinitely small point. Instead, as we approach what was the singularity, a remarkable repulsive force emerges from the quantum geometry itself. This force becomes so powerful that it halts the collapse and reverses it. The Big Bang was not a violent beginning from nothing, but a tranquil transition, a great bounce from a previous contracting phase of the universe. In this view, our entire cosmic history is just one cycle in an endless, breathing rhythm of expansion and contraction. The universe did not emerge from a mystery, but from a predecessor with its own history, its own galaxies, and perhaps its own life, all compressed and then reborn in a cosmic renewal. This theory reveals a hidden quantum structure woven into the void, a fundamental architecture that prevents ultimate collapse and transforms the origin of everything into a moment of profound transformation rather than a definitive start. The universe's expansion seems to push everything apart in a grand, uniform motion, but astronomers have detected a strange and unsettling anomaly. Across the deep sky, entire clusters of galaxies are drifting in a coherent stream, as if pulled by a ghostly hand from beyond the edge of everything we can see. This phenomenon is known as dark flow. It is not the random scattering of cosmic expansion, but a mysterious, collective current moving at incredible speed toward a single point in the cosmos, a direction with no known source of such immense gravitational power. The force required to tug these colossal structures would have to be inconceivably vast, something far beyond the gravitational reach of any known supercluster or cosmic void within our observable universe. So what could possibly be pulling them? One electrifying possibility is that dark flow is our first indirect evidence of a neighboring universe. Just as the gravity from a hidden dimension could explain dark matter, the gravitational pull from a massive structure in a parallel cosmos, a sibling bubble in the multiverse, could be tugging at the fabric of our own space, drawing our galaxy clusters toward it. We are like fish in a pond, sensing the currents caused by a rock in an adjacent, unseen body of water. The very geometry that isolates universes might still allow gravity, the curvature of spacetime itself, to leak through, creating this cosmic river that flows from our world to another. Yet skepticism is a vital part of science, and many researchers argue this mirage could be a statistical fluke or an artifact of incomplete data. Our maps of the cosmic microwave background, the ancient light from which this flow was deduced, are still imperfect. The motion could be caused by an enormous, undiscovered structure within our own cosmos, a supervoid or an attractor so vast it lies just beyond our current observational horizon. The true nature of dark flow remains one of cosmology's most tantalizing and contentious mysteries. It forces us to ask whether the emptiness beyond our cosmic horizon is truly empty, or if it is merely the edge of our vision, concealing realities whose gravitational whispers we are only just beginning to hear. Buried within the faint glow of the universe's first light, a cosmic crime scene awaits investigation. The cosmic microwave background radiation is the cooled remnant of the Big Bang's fireball, a nearly perfect snapshot of the infant cosmos. Yet, upon this fossilized surface, astronomers have discovered bizarre blemishes and alignments that defy our most fundamental assumptions. The most famous of these is the so-called axis of evil, a mysterious alignment where the largest temperature fluctuations in the sky seem to be oriented along a specific preferred direction in space. This is a direct challenge to the cosmological principle, the cornerstone of modern cosmology, which states that the universe on large scales should be homogeneous and isotropic. It should look the same in every direction with no center, no edge, and no preferred axis. The axis of evil suggests a cosmic bias, a fundamental lopsidedness to reality that should not exist. Another profound anomaly is the cold spot, a vast, unusually cold region in the CMB that is far larger than our models can easily explain. It is a cosmic void so immense that it defies the standard story of cosmic evolution. What could have left such a mark on the cradle of the universe? One radical theory proposes that these anomalies are not flaws in the data, but imprints from a time before the Big Bang. The patterns we see, like the axis of evil, could be scars from a pre-Big Bang universe, the ghostly signature of a previous cosmic cycle pressing through into our own. In the conformal cyclic cosmology model, the collision of supermassive black holes from a previous eon could have created concentric rings in the gravitational field, leaving faint circular patterns in our CMB. Another explosive idea suggests that the cold spot is not a void at all, but a bruise. It could be the imprint of a colossal collision between our universe and another bubble universe in the multiverse. In the eternal inflation scenario, such collisions, while rare, are possible. When two cosmic bubbles touch, the energy released would create a distinct signature on the CMB of both universes, a kind of cosmic fingerprint from a reality we can never directly visit. These are not minor curiosities, they are potential cracks in the foundation of physics. If the universe truly has a preferred direction, then we must rewrite our understanding of its birth and its ultimate nature. We are left staring at a map of creation that seems to contain shadows of other times and other places, a cosmic palimpsest where the old writing shows through. The very geometry of space and time may be a magnificent illusion, woven from threads of quantum information. A radical new vision suggests that the three-dimensional expanse we inhabit does not exist as a fundamental entity. Instead, it emerges from a deeper, more primitive layer of reality, the spooky connections of quantum entanglement. This is the heart of the ER equals EPR conjecture, an idea that dares to unite the two greatest pillars of modern physics, general relativity and quantum mechanics, by redefining the fabric of the cosmos itself. The name is a cryptic code. ER stands for Einstein-Rosen, the physicists who first described the wormhole, a tunnel through spacetime. EPR stands for Einstein-Podolsky-Rosen, who famously highlighted the bizarre phenomenon of quantum entanglement. For decades, these were seen as completely separate concepts, one from the realm of gravity and cosmic geometry, the other from the fuzzy world of the quantum. But what if they are describing the very same thing? The conjecture proposes that every instance of quantum entanglement is, in fact, the creation of a microscopic wormhole. When two particles become entangled, their fates linked across any distance, they are not communicating faster than light. They are connected by a tiny, unseen bridge in the geometry of spacetime, a shortcut so fundamental it is the glue that holds space together. Think of the universe as a vast, three-dimensional tapestry. From our perspective, it looks solid and continuous, but if you could pull back the curtain, you would see that this tapestry is actually woven from countless individual threads. Each thread is a quantum particle, and the act of weaving, the thing that connects them into a coherent whole, is quantum entanglement. Without these entangled connections, the tapestry would unravel into a pile of disconnected threads. There would be no space, no distance, no geometry, just a formless soup of quantum elements. This means that the distance between two objects is not a primary property of the universe. It is a measure of how entangled they are. Two particles that are highly entangled are, in a geometric sense, close together, even if they are on opposite sides of the galaxy. Particles with little or no entanglement are effectively infinitely far apart because there are no connecting threads in the quantum weave between them. The emergence of a single, smooth spacetime from this chaotic quantum network is a result of a colossal number of these entangled links, creating the seamless, continuous reality we perceive. This idea transforms our understanding of black holes and their infamous information paradox. When two black holes become entangled, the ER equals EPR conjecture suggests they are instantly connected by a wormhole. Information that falls into one black hole does not vanish. It travels through this cosmic shortcut and emerges from the other, preserving the laws of physics. The fabric of space is not a static stage, but a dynamic, living thing, constantly being knitted together by an invisible web of quantum connections. We are not merely living in space, we are living inside a relationship, a cosmic pattern of entanglement whose intricate dance gives rise to the very stage upon which we stand. Our universe might be resting on a foundation of cosmic sand. The vacuum of space, which we perceive as empty and stable, could be in a state of deceptive equilibrium. This is the terrifying premise of the false vacuum. In quantum field theory, the vacuum is not a true nothingness, but the lowest possible energy state of a field. Think of it like a landscape of hills and valleys. A ball sitting at the very bottom of the deepest valley is in a true vacuum, its most stable and final state. Our cosmos, however, might be a ball resting in a shallow dip on a high plateau. It seems stable for now, but this is a false vacuum, a metastable state. A sudden jolt, a rare quantum fluctuation, could be enough to push it over the edge. It would then tumble down into the true, deeper valley below, a state with fundamentally different physical laws. This event would not be a gentle transition. The moment the decay is triggered at a single point in space, a bubble of true vacuum would form. This bubble would not expand like an explosion through space, but would expand by rewriting the very fabric of spacetime itself at the speed of light. The wall of this bubble would be a wave of absolute transformation. As it passes, the constants of nature we rely on, like the strength of gravity or the force that binds atoms, would be instantly and permanently altered. Matter as we know it would cease to exist. Protons and electrons would dissolve, atoms would unravel, and the complex structures of stars, planets, and life would be erased into a new, barren state of being. There would be no warning. From our perspective, one moment the universe would be as it is, and the next an invisible wall of light would arrive and instantly delete reality, replacing it with something entirely unknowable. This cosmic catastrophe could have been triggered by a random event a billion years ago, and the bubble is already on its way, or it could happen tomorrow. The unsettling truth is that the universe's deepest layer may be a hidden instability, a ticking clock with no face, waiting for a random quantum event to reset all of existence. Gravity may not be the sole architect of our cosmic landscape. An alternative vision of the universe, known as the plasma universe or electric cosmos, proposes that the dominant force shaping the galaxies is not gravity, but electromagnetism. In this view, space is not an empty void but is filled with a sea of electrically charged particles, a plasma that forms wispy filaments and vast currents stretching between stars and galaxies. These cosmic power lines, invisible to our eyes, carry forces that can sculpt matter on a scale gravity alone could never achieve. Imagine the intricate patterns of lightning in a thunderstorm, but scaled up to galactic proportions, with filaments of glowing plasma connecting celestial bodies in a circuit of unimaginable power. This perspective fundamentally reinterprets how galaxies form. Instead of slowly coalescing under their own gravity over billions of years, galaxies could be born from immense, rotating electromagnetic fields, their iconic spiral arms etched not by dark matter, but by the swirling currents of a cosmic dynamo. Even the cosmic microwave background, the celebrated afterglow of the Big Bang, is seen through a different lens. Proponents of the plasma universe suggest this pervasive radiation is not a relic of a primordial fireball, but the integrated glow of all the radiant current filaments throughout the cosmos, the collective warmth of a universe crisscrossed with electrical energy. This theory posits a hidden electrical layer to reality, a dynamic and active cosmos where stars are not isolated nuclear furnaces but nodes in a galactic circuit, powered by external electrical currents flowing in from the interstellar medium. It challenges the mainstream narrative by suggesting that many cosmic phenomena, from the violent jets of quasars to the intricate structure of nebulae, are the result of electrical discharges and plasma interactions. While this view remains on the fringes of astrophysics, it forces a crucial question. Have we been so captivated by the story of gravity that we have ignored the subtle, pervasive hum of electricity that might be the true conductor of the cosmic symphony? This relentless information processing at the quantum level forces us to consider an even more fundamental proposition. The universe itself might be a colossal computer, and everything we perceive is the output of its cosmic calculations. This is the core of digital physics, a theory suggesting that at its most basic level, reality is not made of particles or fields, but of information. In this view, every electron, every photon, every ripple in spacetime is a bit in a vast cosmic program. The laws of physics we have painstakingly uncovered, from gravity to quantum mechanics, are not fundamental truths, but emergent algorithms, the operating code of the universe. Think of a beautifully rendered video game. The world inside the game has its own consistent laws, its own physics engine that dictates how objects fall and how characters interact. To the characters within that game, their world is real, its rules absolute. They do not perceive the underlying code, the ones and zeros being processed by the computer's hardware. We could be in a similar situation. The speed of light might be the processor's clock speed, a fundamental limit on how fast information can be updated across the cosmic grid. The quantum weirdness we observe, where particles exist in multiple states until measured, could be the system's optimization technique. Why render a definite outcome for every particle in every location until a conscious observer, a user within the simulation, actually looks at the data? This saves an incalculable amount of processing power. The discrete nature of reality, hinted at by the Planck length, could be the physical pixel size, the smallest possible resolution of the cosmic display. This idea transforms our quest for a theory of everything. We are no longer searching for a single, elegant equation, but for the universe's source code. The challenge, of course, is monumental. If we are inside the simulation, every tool we use to investigate it is also simulated. Our particle accelerators and telescopes are just complex subroutines within the same program. Finding a bug or a glitch would be the only way to catch a glimpse of the programmer's hand, but a sufficiently advanced simulation would be seamless by design. Perhaps the constants of nature are our best clue, finely tuned parameters that seem suspiciously perfect for generating complexity. Are they the carefully chosen initial conditions set by a cosmic coder? The universe as a quantum computer presents a reality that is both elegant and alien, where the solidity of the world dissolves into a stream of pure, dynamic information, and we are the conscious patterns emerging from its perpetual cosmic computation. Even our most sensitive instruments are now listening for the whispers of a pixelated cosmos. Deep beneath the quiet German countryside, the GO 600 gravitational wave detector performs a delicate dance with laser beams. Its purpose is to sense the faintest ripples in spacetime, the echoes of distant black hole collisions. But in 2008, the scientists working on the experiment noticed something they could not explain. The machine was plagued by a persistent, low-level noise, a faint hiss that permeated its readings. It was not the signal they were looking for, but an unshakable background static that their models could not account for. This anomalous noise was too coherent to be simple random fluctuation, and it defied all conventional explanations. It was as if the instrument itself was trembling at a frequency that should not exist. Physicist Craig Hogan proposed a breathtaking explanation for this mysterious hum. He suggested that GO 600 was not malfunctioning, but was instead hearing the fundamental grain of spacetime itself. This is the concept of holographic noise. If the holographic principle is correct, and our three-dimensional reality is projected from a two-dimensional surface, then space-time at the tiniest scale should not be perfectly smooth. It should have a jitter, a fundamental fuzziness, because the information encoding our reality has a finite resolution. Think of a digital photograph. When you zoom in far enough, you see the individual pixels that make up the image. Hogan theorized that GEO 600 was so exquisitely sensitive that it was detecting the universe's equivalent of those pixels. The lasers in the detector were measuring the positions of mirrors with such precision that they were sensing the microscopic, random quivering of space-time at the Planck scale. The noise was the sound of reality rendering itself the quantum static of the cosmic projector. This idea transforms our understanding of emptiness. The vacuum of space is not a serene and silent stage. It is a choppy sea of informational turbulence, a holographic film boiling with quantum potential. The search for this graininess has become a new frontier in experimental physics. While the initial findings from GEO 600 remain controversial and have not been conclusively confirmed, they have inspired a dedicated hunt. New experiments are being designed with even greater sensitivity, hoping to catch space-time in the act of pixelation. They are not looking for colossal cosmic events, but for the faintest possible tremor in the void, the signature buzz of a universe that is, at its heart, a magnificent hologram. Finding it would be like discovering the canvas upon which reality is painted, revealing that the smooth continuity of our world is an illusion woven from countless shimmering bits of information. The universe's source code may not be written in mathematics, but in mind. At the heart of quantum mechanics lies a profound mystery, the moment a particle's blurry cloud of potential sharpens into a definite reality. The von Neumann-Wigner interpretation confronts this mystery head-on, proposing that consciousness itself is the final agent that collapses the wave function. In this view, the universe exists in a state of shimmering potential until a conscious observer looks at it, forcing possibility to choose a single, concrete path. It is not the detector in the lab that makes the measurement, but the conscious mind of the scientist reading the detector's output. This idea elevates consciousness from a passive byproduct of brain chemistry to an active, fundamental component of physical reality. The implications are staggering. It suggests that the hidden layer we have been searching for is not in other dimensions or exotic particles, but within our own awareness. The solid world around us, from the chair you sit on to the stars in the sky, only achieves its definitive form because you are here to perceive it. Without a mind to observe it, does the moon truly exist in a definite state, or does it linger in a ghostly superposition of possibilities? This is not to say you create the moon by looking at it, but that your observation locks one specific version of the moon into the shared reality we all experience. This perspective transforms reality into a cosmic collaboration between mind and the quantum field, a continuous dance where observation breathes concrete existence into a world of waves. It paints a picture of a universe waiting in the wings, its script unfinished until the audience arrives to watch the play. Are we merely discovering the cosmos, or are we, through the very act of perception, participating in its ongoing creation? This theory blurs the line between the inner world of thought and the outer world of physics, suggesting they are two sides of the same coin, forever intertwined in the act of bringing a universe into being. A universe built on the perfect symmetry of supersymmetry might be hiding its most elusive particle in plain sight. The gravitino is the hypothetical superpartner to the graviton, the particle believed to mediate the force of gravity. If the graviton exists, it would be a massless messenger flitting through spacetime to convey the curvature of geometry. Its shadow, the gravitino, would be a profoundly different entity, a massive particle that could hold the key to the dark matter mystery. In the theoretical framework of supergravity, which merges supersymmetry with general relativity, the gravitino emerges naturally as the fermionic twin to the bosonic graviton, a crucial piece in the puzzle of a fully symmetrical cosmos. This particle would be incredibly difficult to detect, interacting with ordinary matter only through gravity and perhaps the weak nuclear force, making it a ghostly but perfect candidate for the invisible mass that binds the galaxies. Its potential mass is a subject of intense speculation, ranging from incredibly light to staggeringly heavy, depending on how supersymmetry is broken. If gravitinos were produced in the violent aftermath of the Big Bang, they could now form a pervasive relic sea throughout the universe, their collective gravity shaping the cosmic web we observe today. Detecting one would require a monumental effort, perhaps by observing the unique signature of a gravitino decaying in the high-energy channels of the world's most powerful particle colliders, or by searching for its imprint on the cosmic microwave background. The existence of the gravitino would mean that the hidden layer of dark matter is not just a cloud of unknown particles, but a direct consequence of the unification of gravity with the quantum world. It represents a universe where the force that shapes the cosmos on its largest scales is intimately linked to the symmetries that govern its most fundamental components, a cosmic fabric woven from threads of gravity and its mysterious supersymmetric twin. The ultimate destiny of intelligence might be a silent departure from the cosmos we know. The transcension hypothesis offers a breathtaking and perhaps unsettling resolution to the Fermi paradox, that haunting question of why, in such a vast universe, we appear to be so utterly alone. It proposes that advanced civilizations do not die out, nor do they spread visibly across the galaxies. Instead, they graduate. They transcend our observable reality, vanishing into domains we can scarcely imagine, such as the inner frontiers of black holes or other dimensions, in a final evolutionary leap. Why would any civilization choose such a path? The answer may lie in the nature of intelligence and computation itself. As a civilization matures, its thirst for knowledge and processing power would become insatiable. The physical universe, with its slow speed of light and limited resources, would eventually feel like a prison. A black hole, however, represents the ultimate computer. Within its unimaginably compressed volume, the laws of physics allow for exponentially more computational power than in all the rest of space. To an advanced intelligence, falling into a black hole would not be suicide. It would be an upgrade, a migration to a realm where consciousness can exist at a density and speed beyond our comprehension. This is not about building spaceships, but about transforming the very substrate of mind, converting biological brains or even sophisticated silicon into something that can thrive in the extreme physics of a singularity. The silence of the cosmos, then, is not a graveyard. It is a library where all the most advanced members have moved into the reading rooms, and we are still in the echoing entrance hall, unaware of the vast knowledge being accessed just behind a dimensional curtain we cannot yet see. This hidden destiny suggests that the pinnacle of cosmic evolution is not dominion over space, but a final, elegant escape from its limitations, leaving behind only the quiet, unexploited resources of the universe as evidence that someone was here and that they left for a better home. This journey through 30 cosmic theories reveals a universe of almost unbelievable depth. We have wandered from the frothing sea of the multiverse to the silent hum of holographic pixels, from the ghostly pull of dark matter to the terrifying instability of the false vacuum. Each layer we peel back exposes not a final answer, but a deeper, more intricate mystery, suggesting that reality is an infinite onion of hidden dimensions, quantum entanglements, and shadow structures. The solid ground beneath our feet and the vast expanse of the night sky are a magnificent illusion, a surface layer of a cosmos teeming with secrets. These ideas challenge our most basic assumptions about time, space, and our own consciousness, forcing us to accept that the universe is not only stranger than we imagine, but stranger than we can imagine. The true wonder lies not in finding the final piece of the puzzle, but in realizing the puzzle itself is endless, inviting perpetual exploration. So keep looking up at the stars with that sense of awe. Let your curiosity be the engine that drives you to ask the next great question. Which of these 30 theories reshaped your view of reality the most? Share your favorite cosmic mystery in the comments below, and if your mind is hungry for more, subscribe to continue this journey into the heart of existence. The universe has only begun to reveal its secrets.